Swayam Prabha. Digital India. Educated India.
So, good morning everyone, and welcome to this course, GN course on modeling and simulation of granular systems. My name is Ratna Kumar. I am a faculty member in the Department of Mechanical Engineering at IIT Madras. And first of all, thank you very much for choosing to join this course. And this course will be primarily taught by Professor Zhidong Zhao from Hong Kong University of Science and Technology. Unfortunately, his visa could not be issued in time, and hence we had to convert this course, which could have otherwise been an in-person course, as a hybrid course, wherein I will be delivering lectures in person here, and Professor Zhao's lectures will be online. And so, we will find some other opportunity to invite Professor Zhao to IIT Madras, where we can have an opportunity to interact with him in person. And I should thank Professor Zhao for agreeing to do this online, although he has been waiting patiently for the visa for last 1 month. Yeah. So, with that short introduction, first of all I would like to start by acknowledging a few people. First, Professor Zhao for accepting this invitation to offer this course on modeling and simulation in granular materials. He is a very well known figure in the granular mechanics community, particularly from the modeling perspective, and hence his lectures will be of high value to all of us, where we get to learn the techniques of modeling and simulation in granular systems from an expert's perspective. And then I would like to thank the code office and JN team at IIT Madras for hand holding us through the entire process and ensuring the registration process and all went smooth. And then the JN national coordinator IIT Hyderabad for helping us taking care of all the registration details and paperwork particularly, so that we could focus on only the course. And Ministry of Education for conceiving this great idea of offering courses particularly at the graduate level through the experts across the world. So, that would be very valuable for PhD students and faculty members who want to get into this area. And I also would like to thank Altair India for providing us EDM licenses, and participants will be exposed to this software through practical sessions during the course of during the 1 week course on this particular topic. Department of Mechanical Engineering at IIT Madras for providing us the room where, while we had difficulty in finding a venue for this course. Last but not the least, I would like to thank Shakti and Amiya, my PhD student and postdoc, who helped us do all the nitty gritty works, and some of you might have got help from Shakti for your accommodation, and they will be taking care of laboratory sessions. Both you will have mostly computational, but they may also show a few experiments. Okay. So, first of all I would like to give a very quick background or introduction of Professor Zhao before I start the course. Professor Zhidong Zhao is a professor of computational geomechanics in the Department of Civil and Environmental Engineering in Hong Kong University of Science and Technology, and he is also the director of computational granular mechanics lab at Hong Kong University. He is also holding a chair, Chang Jiang Scholar Chair professorship conferred by Ministry of Education in China. So, Professor Zhao received his bachelor's and PhD degrees from Tsinghua University in China, and he is very well known for his groundbreaking research in the computational geomechanics and granular mechanics in general, which is quite evident from several of his accolades and some of his contributions in the form of co-editor of computers and geotechniques, and also as an associate editor of Journal of Engineering Mechanics. He is also editor of the popular journal in this area, Granular Matter, and also on the editorial boards of several other journals. Alongside these editorial services, in recognition of his service to the computational granular mechanics community, he is identified as one of the top 5 cited articles in Granular Matter, and in 2021 he also received the first received a first class in natural sciences for Ministry of Education Higher Education Outstanding Scientific Research Output Award. And no, I have not changed the slide. Yeah, I am just introducing Professor Javo. Okay, I think with that introduction, we understand Professor Javo's contribution in this area, and we look forward to hearing his lectures. So the lecture plan for this course is as follows. I will be teaching the introductory part today in the morning session up to first session, and Professor Javo comes in the second session, basically at 11:30, and then 11:30 to 1 o'clock. And tomorrow I will take care of the contact models module, and the later parts will be taught by Professor Javo. So Wednesday, Thursday, Friday will be taught by Professor Javo. So that is the plan, and with that initial introduction, shall we go ahead and start? So if there are several online participants, as I see. If you have a question, please raise your hand, then one of our TAs will be observing the room, and if there is a question, then they will interrupt me, then I will try to answer the question. And when you are given an opportunity, then please unmute your microphone before speaking, so that there is no delay in the process. Yeah. So Jidong, so it is up to you. If you want to stay back, you can stay, otherwise you can join at 11:30 as per the plan. I will send you a message, but if you are online and if you can stay, that will be great, but either way is fine, because I understand that you may have some other commitments. Yeah.
Thank you, Professor Ratna. Thank you for the kind introduction, and it's also my great pleasure really to have the opportunity really to give this GIM course, and then I look forward to really to interacting with all the class here. Thank you.
Let's get started. As we are going to talk about the topic of modeling and simulation in granular systems, first of all, let's try understand what granular systems are. Right. So let's start with the definition of a granular material. A granular material is a conglomeration of discrete macroscopic particles characterized by loss of energy when the particles interact. That is the general definition of a granular material. It is basically a collection of numerous discrete macroscopic solid particles. We are not really talking about the particles at the atomic scale, we are really talking about macroscopic particles. So the examples are, for example, ball bearing in milling soil, powders, coal, grains, pharmaceutical tablets, ore, rock, etc. Everything and anything under the sky is in a macroscopic form can be seen as granular material. So when particles interact, so they dissipate energy. We will discuss about it. So that dissipation is the key characteristic of a granular material. So the granular materials, where they are ubiquitous, they are everywhere. You can see the cereal, here the wheat grains that are shown here. These are not tablets, but these are chocolates, some kind of chocolates. And here you can see the famous Mumbai suburban train, wherein people try to get in during peak hours, right. So if you would take a bird's eye view, and you can actually see each person as a particle, and then see how this movement dynamics is happening. So people have modeled these kind of systems using granular dynamics approach, right. So, for example, recently we had Kumbh Mela, right. So, there's millions of people visited Kumbh Mela in Allahabad, right, Prayagraj, and the movement of these people, when there are too many people in a small confined space, how this movement can be accommodated. For example, if you look at this particular GIF image, you would see that there are some people who are putting in more effort to get in, there are some people who are not putting any effort. So, you just have to stand at the right spot in order to get in easily. If you are not at the right spot, you are actually experiencing the entire stress from the other people, right. If you are smart enough, you know where to stand and get in without much of a difficulty, right. Again, you can see here the sand castle, which is also a granular system. We know in this in the beach, we as kids we would have built some castles like that, or now if some of you are married, your kids must be doing that. Again, so you can see several pebbles which are found on the shores of beaches or rocks or kind of granular materials. Here you can see pharmaceutical tablets. The reason why I said microscopic, we are actually talking about particles of this kind in this course, although the principles can be applied to particles at much smaller length scales, which we will see some of the examples that we will show during the course involve particles whose sizes are few microns, particularly in the area of additive manufacturing and so on, right. So, but the idea is that the granular material, why this is an important area of study, because they are everywhere, and the most important part of these materials is that they do not behave as we expect them to behave. What do we mean by that? So, if we ask a question, are these granular materials solid like or liquid like? So, how do we answer this question? Are they solids? They are granular solids, they are all solids, right. But the collective behavior, will it be solid like or liquid like? So, let us take one example, a very simple example that is close to our hearts. So, all of us must have opened a pack of grains at home, right. How do we do that? We cut at a corner and then try to pour the pack of grains into a container. When you do that, if you do not cut properly, if your hole size is not large enough, then what happens? Initially the particles flow, then after some time what happens? There will be clogging. So, if you look at this system as a granular system, initially they have behaved like liquid because they are flowing, but after some time they are clogging, after some time that is not flowing, very similar to how a solid behaves like. So, the granular systems, depending on the context, they might behave like solids or they might behave like liquids. So, that is what makes these systems extremely complex, because we do not really understand how and when they try to behave like solids and when they try to behave like liquids. And if you want to develop a theory to describe these systems, the theory will be complex, because we have to change our understanding, our description of solid like behavior to the liquid like behavior depending on the context, right. So, why this is interesting for us as engineers? Because these granular materials are everywhere across various industries. So, for example, you have additive manufacturing, agriculture, cement production, construction. Some of you are civil engineers who deal with concrete, soil, sand and so on, and mining, pharmaceuticals, silos and production of steel and even thermal energy storage, and the granular systems are also seen in popular lithium ion batteries. Lithium ion battery electrodes are granular materials, right. If you look at the electrode, they are granular materials, but they are bound together through a binder. But the principle of granular materials is extremely useful in understanding the reliability of lithium ion batteries. So, if you look at mining industry, so the excavation process and transportation of coal, for example, it's a granular system that you need to find ways and means to transport this in the best efficient way with the minimal energy cost. So, here I will show you couple of videos which actually show the interesting or rather complex behavior of granular systems. Here the first video I am showing here is a snow avalanche, which is a collective behavior of these particles, and then how that can create a havoc in a system. So, let us look at that. So, you can see here you have a ground station.
Bara beklaga att jag själv lite här på filmen. Det är snö som kommer ner. Det är inte bara stör ser det ut den här gången. Det blir spännande att se för det såg ut som det gick en stråle rätt i texten.
The voice that we are hearing is from the other end of this lake.
Kommer snöfocken ganska fort. Jag tror den avbryts väldigt snabbt.
So, this is another example where this is silo storage, where food grains are stored in these silos, right. So, if you they look very stable, but if we don't do things right, then they can create havoc. Like in the former case, we have seen a natural disaster. A similar thing happens when you have landslides. That is very much that is very well known to geotechnical engineers, how landslides happen. And when they happen, the kind of devastation that they cause is enormous. So, if we are able to understand how these landslides or stability can be controlled by proper intervention, right, then one could reduce the kind of loss that happens during these natural calamities. So, here another example of silo storage. So, let us look at this video and try to understand what is happening. So, there was a initially small crack that happened, and the person in charge was there trying to fix it by closing it, but because although it is a small crack that has started, and you can imagine the kind of load that you are talking about, a silo whose height is tens of meters, and then suddenly the entire thing is collapsing, and the amount of force that it exerts in order to push away the truck that is there, and it probably can take several lives, right. So, here another example where one needs to handle granular systems carefully is in ash handling plants. This is typical in several power plants, right. So, thermal power plants where one needs to handle coal and ash carefully, and in order to reduce the pollution to the surrounding environment, one needs to understand how can one reduce the transfer of these particles over large distances, right. So, this is something that is known to happen in various thermal power plants, right. So, the other industry where we see granular systems, the knowledge of granular systems being important is pharmaceutical industry, wherein you have the need for doing proper mixing of APIs and binders and excipients, and unless we mix them properly, you will not be able to get the good quality tablet out. So the mixing process, although it looks pretty simple, but the amount of energy consumed in the mixing process and ensuring that homogeneous composition at any small sample is a complex problem. So people spend, even today, people spend lots of money in developing the most efficient mixers, which can consume less energy, but ensure uniformity in the composition in a given granular systems, right? So the powder mixing, dye filling, and tablet coating, these are all important problems, still needs to be fixed. So whenever you have a tablet, when you are compacting a tablet is made through compaction of the powders, right? When you are compacting a tablet, if you see a crack in a tablet, do we consume it? When we buy a tablet, if we see a physical crack in the tablet, do we consume it? We don't. Although it did not lose its medicinal characteristics. It is just that the consumer mindset that when you see a crack, you think that it is not useful. Although medicinally it has not lost its value, but for the company, having a small crack is loss of money. So how can we develop manufacturing processes which involve granular systems to reduce the amount of wastage, right? The other area, few more areas, like for example, so you see agriculture sector. So we know that the soil inversion is an important step in laying new crop every season, right? And then efficient soil inversion over large fields takes a lot of time. And the equipment that we design, if we can improve the inversion efficiency of these equipment when they are working on a different soil, different kinds of soil terrains, that helps improve the productivity, right? So which means we need to understand the interaction between the soil and the machinery. And the soil is not uniform everywhere. It has different particle size distributions. It has different cohesion properties. That means the water content is different at each and every location. And how do we improve the soil inversion efficiency when the soil is interacting with the machinery? That's an interesting granular mechanics problem which deals with understanding the granular properties. At the same time, you want to enhance the life of the machine, right? So that means because there is an erosion, the material, the granular material and steel interaction will lead to wear and tear of the machinery. How can we minimize that? At getting the maximum inversion efficiency is something of interest for agricultural industry. Similarly, in blast furnace, in steel making, you use blast furnace. When the blast furnace charging takes place, one needs to employ granular mechanics principles in order to enhance the efficiency of the charging process in the steel in the blast furnace. There are other systems like thermal energy storage. Phase change materials are used for thermal energy storage. For example, if you are dealing with solar energy, you have only the energy can be extracted only in the mornings when the sunlight is there. But when there is no sunlight, how do you continue to supply the energy? You basically store the energy in some sort of phase change materials, which are again granular in nature. And this integrity of these granular systems is extremely important in order to ensure the long-term thermal energy storage capability of the system, right? And cement industries, we know a lot of granular interactions that take place. There are a lot of mixing that happens. And not only that, not only about the production process, but about the pollution that the industry might create because of the flying of small particles and so on. And the industry is required to address these issues. So for example, if you go to a thermal power plant, so in thermal power plant, one of the major issues is when the ash comes out, and they need to continuously wet the ash so that the ash does not fly to the surrounding places. It's a serious problem. Many of us don't realize because we don't live close by. But if you happen to live close to a thermal power station, you understand your house is full of ash every day on the floors. So this is a serious problem, and it can also cause serious medical conditions. So we need to develop techniques how this transport of these particles over large distances can be minimized. So what are the interventions? One of the simple interventions that people use is to add water to these particles so that the cohesion between the particles is increased and hence their transportation is minimized, right? But this also has limitations, so one needs to see how to overcome such limitations. And recent advancement in manufacturing technology such as additive manufacturing, particularly one of the techniques called laser powder bed additive manufacturing, wherein powders are used as the raw material, and then those powders are either sintered or melted to create components, right? So the powder spreading, so how do you create a powder layer on the bed is an interesting area of to study, because the powder layers quality in terms of how the particles are arranged. Do we have uniform porosity everywhere? Is the powder layer uniformly packed everywhere? If not, depending upon the location where you are sintering or melting, you may have a different kind of quality of the product. So one needs to understand how one can ensure the uniform powder quality in the entire bed when you are developing your spreading technology, right? These are the kind of areas that one would look at. So as I mentioned, they are neither solids nor fully liquids. They behave somewhere intermediate. So they may start behaving like liquids and suddenly they start showing solid-like phase. And sometimes they may be looking like solids and suddenly they behave like liquids, such as the case of snow avalanche that we have seen, right? Landslides that we have seen. They are solid-like, but suddenly when the right conditions meet, which are not right for us, but for it to become liquid, then the right conditions are met, then the solid-like system starts behaving like liquid and you have devastation. So that is the complexity that is involved in understanding these materials. So when we want to design industrial systems that involve granular materials, we need to keep these complex behavior of granular systems in mind and think about optimizing the process so as to ensure safety and efficiency. So this is a one interesting video that actually shows how a granular system can transition from a solid like to a liquid like. So you see what's happening. So you have a sand bed. Initially it is not excited with any external force and it behaves like a solid, and then they were actually exciting this sand bed from the bottom. So they are actually putting it on a shaker table like thing. So it is giving some vibration signal from the bottom, because of which the strong contact forces that were there between the particles got loosened up, and hence the particles behave like liquid. So then you could see that they are able to push their hand inside the soil sand as if they are actually keeping their hand in water, right? So depending upon the context, depending upon the boundary conditions that the granular system is subjected to, it can change its phase from being a solid to a liquid and vice versa. The moment they have stopped the vibration from the bottom, from the base, at the base, again simply it stopped being a liquid and it started behaving like a solid, right. So, that is one of the nice ways to show how a granular system behaves from solid state to liquid state and vice versa. So, the idea is that, so you could the reason if you apply forces at the bottom, right. So, what happens is on the top surface you have a free surface. So, there is nothing that actually constrains the motion. You want to free up these particles so that there is no confinement that is stopping these particles to move around. So, when you are giving excitation from bottom, the chains, I will talk about the force chains are disrupted, and hence on the top there is no constraint, and hence the particles are finding it easy to move around, and that is what is making them behave like a liquid. So, if you are applying force from the top, right, then at the bottom it is constrained again, right. So, you may not see that behavior, right. But if you are applying force from sides, you may see some kind of a variation, but bottom, because if you are applying force in this direction on the top surface, it is completely free. So, the particles can jump around, right, that is that. So, when we talk about designing granular systems, we have to keep in mind of their characteristics. The first and foremost characteristic is that they are discrete in nature. So, I am sure a large fraction of you would have heard about a continuum approximation, right. You use finite element method, wherein we deal with simulating the continuum behavior of the system. So, we actually do not talk about material having disjoint unless we have a crack in the material, right. So, these are called continuum materials, that means you do not consider voids at the particle level. There is no gaps between the particles, and the particles are strongly connected. That is how a solid is defined. Whereas, if you are looking at a granular system of particles, of solid particles, please keep in mind that individual solid particle is still behaving like a solid, but the collection is what is making them complex, to behave complexly. So, the collection of these solid particles is what making our life tougher, but individual solids still behave as if they are solids, because the atoms are tightly bound within each solid, right. So, as a collection they are discrete in nature, which basically means that these particles, depending on the situation, they may talk to each other or they may not talk to each other. Like in the case you have seen of the Mumbai train example, right. Sometimes when the people are touching each other, and after some time they are not touching each other. So, each one of them as a particle. So, sometimes they push together to get in, and then sometimes they come out when they need not touch each other. So, the particles may change their neighbors. So, today if you are extremely dynamic granular system, you may change your neighbor every fraction of a second. So, that means they are discrete in nature, they are not keeping their neighbors the same. In a continuous system, you do not expect to change your neighbor that often, right, unless there is a crack in a material. So, as a result, the constitutive response of these materials will be different from conventional continuum materials. So, when we are talking about this bulk of the granular system, that means a collection of these solid particles, their behavior is governed by what these individual particles are made of. Let us imagine for some time all these particles are made of same material. Okay. For example, if you take sand, so collection of sand particles is a granular system. Now, the behavior of this granular system depends on the bulk property of the sand, which means what is the mechanical property of the sand, each and every individual sand particle. Okay. So, imagine a scenario. So, let us do this thought experiment. You have a container. In the container, It's a circular cylindrical container. In the container, let us keep one block of steel cylinder, steel cylinder, all right, and imagine you are compressing it. You are applying a compressive force on the block of steel. So, let me do this thought experiment for you. So, if this entire thing is steel, apply a load. That is the thought experiment I am doing. Exactly same kind of cylinder. Now, fill this cylinder. It is steel, but not with filled with steel block, but I am filling it with steel balls. Okay? The material is the same, except that in the first case it is a continuous steel block, and here I have steel balls. Okay. So, now I have a piston and I am applying a force on these two. So, now what do you expect? When you are applying this force or when you are applying a displacement, when you are pushing it, you will feel some resistance, right? Isn't it? So, that is what we typically call a force displacement response, isn't it? So, what do you expect? Do you expect to see same force displacement response in these two cases? It is steel only, no? The block is also steel, the material is also, the balls are also made of steel. Do you expect same kind of force displacement response? Why not? So, there is no movement between the particles, first thing, and the second thing is there is slip that is taking place between the particles, isn't it? Because of that, the macroscopic force displacement response that you will see will be very different in both of them. Now, let us replace these steel balls with bean bag balls. You know what is a bean bag, right? That we used to sit on, thermocol. So, let us replace this with the thermocol balls. What happens? It will be much easier for you to push, isn't it? So, the granular system response, first of all, it will be different from a continuum response because it is discrete in nature, right? So, that is the first point. And the second thing is the behavior depends on the bulk properties, meaning what the particle is made of. It really matters whether the particles are of steel or particles are of thermocol. And the other thing that the macroscopic behavior of such a granular system also depends on other particle properties. What are they? Such as size and shape distribution. Are all the particles are of same size, or you have a particle size distribution? That means some particles are large, some particles are small, right? And what is the shape of these particles? Are they spherical or non-spherical? So, these things govern the macroscopic behavior. Not only that, the interparticle interactions. What do I mean by that? So, imagine you are filling the same container with sand, okay, and take another container, add some water to the sand. Now, what do you expect? Do you expect same behavior or different behavior? We expect different behavior. What did we do by adding water to the sand? We have enhanced. What did we do by adding water to the sand? So, we have introduced interparticle cohesion through the water bridge, right. So, that interparticle interactions, what kind of interparticle interactions do we have also matters, and what type of load that we are applying. Does it behave the same whether I apply a confinement force or a shear force and so on? It depends on at what instance you have, right, because see, for example, if you take a steel block, with the steel block you more or less get linear elastic response, right, because the deformation in the at least until the onset of flash deformation. Whereas with the steel balls, your macroscopic response in general will not be linear. From the beginning it starts to be non-linear. That is one of the major differences. Although the underlying material is linear elastic, but the macroscopic response, when you draw the force displacement curve, it will not be linear. It will be non-linear in general, right. That is one of the key characteristics. But after doing confinement, right, and depending upon the interactions, if the interaction between the particles is so much, that means if you have compressed it to a larger extent, then it may reach the stiffness of the continuum particle, right. But it is very unlikely that it may surpass the macroscopic stiffness, elastic stiffness of the continuum particle. Okay. So this, because the behavior, macroscopic behavior depends on several parameters, that makes it challenging for us to design the systems that involve granular materials, and that is the reason why we are here. So before we actually go about designing something, and we should be able to have tools that allows us to analyze these granular systems, right. So some such tools, one can use the several modeling approaches. One of such modeling approaches which actually takes care of dealing with each and every particle and motion of each and every particle is what we call a discrete element method, and that is what we will focus a lot in this course. But in the literature, people also have shown that although we are interested in understanding how these individual particles behave, but in the end our greater goal is to understand macroscopically what is their behavior. In such scenarios, there were some homogenization approaches which allows us to simulate granular systems as continuum materials using specialized constitutive responses. That means you need to develop a new constitutive response which can represent the behavior of the collection of the particles, which means if I have to represent the macroscopic response of a group of steel particles compressed in a container using a continuum response, the constitutive response will not be sigma is equal to E epsilon, at least in the small strain range. From the beginning it will be some nonlinear elastic response. So what would that nonlinear elastic response be is something that we can address, and people have developed such nonlinear models to describe the macroscopic response of granular materials as a continuum, even though you do not need to, although you are interested in microscopic information, people have looked at what is happening at the microscopic level and then came up with models which can represent the behavior with reasonable accuracy. What are the other areas that granular systems are important for us to understand? So particularly the vehicle tire soil interaction on different kinds of terrains. Lot of work that goes in understanding how tires interact, because the tire itself is a complex material, right. Rubber is one of the most complex materials to actually simulate, and that guy interacting with another complex fellow, a granular material, depending on the terrain, can make our life hell, right. So this is a very interesting area and lot of opportunities in designing systems which are at least understanding the behavior of these systems when the tire soil interactions take place, right. So if you want to, for example, if you understand this, what is the use? Already cars are running on the roads and also off-road vehicles are there, and so what is the use? So if you have a better understanding of these systems, for example, if you want to deploy a rover on Mars, right, you need to understand how the rover wheels interact with the soil and what is the stability condition. So what is if you have designed the vehicle, depending upon the soil conditions, how the vehicle can be maneuvered easily, and similar kind of things. So there are a lot of opportunity in the automobile industry, particularly understanding tire soil interactions, track soil interactions. If you are talking about tracked vehicles, agricultural machinery a large scale agricultural machinery will have tracks. So, how a track interacts with the soil, and it should, can you ensure that the track design is such that it gives the similar efficiency when it is running on a hard soil as well as soft soil? It is not possible, right? But can we do some design interventions which allows, which ensures that reasonable efficiency is guaranteed, right? So, material handling is another area where lot of work has been done, and still a lot of work that is being done, particularly in the area of bulk material handling, where you have to transport, for example, ore, iron ore or coal over large distances without causing loss of material, right? And the difficult part is the granular materials in this case are of not similar size, and their shapes are not nice to deal with. So, how can we ensure that the conveyor life can be enhanced, at the same time not losing material while being transported? So, how do we design the shape and speed of flow, and how do we ensure wear and tear is minimal, and so on. So, this is another area where granular materials play a significant role. This I have already talked about. Fly ash or coal collapse, which is a major concern and particularly an environmental concern, right? So, we need to ensure you have a large ash piles in their backyard, and they need to ensure that they are not collapsing. The moment they collapse, then that can cause several other handling issues. So, how do we ensure, what should be the height of this particular ash pile, and how do we ensure that they are not causing environmental problems? So, these are another area of interest for granular material systems. Again, as I said, they behave like liquids, and here you can see the flow through a chute or a pipe going from a higher diameter to a lower diameter. Depending upon the scenario, the particles can flow, and sometimes, so here the particles are flowing freely, but if you see here, if you look closely, you have something called a popular concept called granular arch, so which actually stops the flow. Until then, the flow continues. The moment an arch like this forms, then it creates a very strong force network which stops the flow, although the weight of the granular system is much larger, which could have broken these forces, but these force chains created are so strong that the granular flow gets stopped. So, how do we come up with mechanisms wherein the flow is uniform? Right? If you are allowing the particle flow through these conveyors, how do we ensure that we have a uniform flow? Where do we have this problem? For example, if you have a bottling plant of some cereals, and you need to ensure that there is no clogging of the pipe through which the particles are flowing. So, how do you ensure what should be the diameter? And you cannot have very large diameter, because then you may not be able to properly pack it, right? And so, the design of these systems is also another interesting area. So far we are only talking about particles flow and particle resisting forces and so on, but granular materials are also extensively used, as I told you, in the case of thermal energy storage for heat transfer applications, right? So, the understanding of the heat transfer of the granular systems. So, here if you look at, this is a granular bed which is heated from the bottom, initially at constant temperature. When you heat it from the bottom, you can see the temperature gradient. At the top it is open to atmosphere and it has maintained certain temperature, and if you continue to send the heat flux, this gas starts heating it up. So, how do you go about simulating such systems, and how does the heat transfer take place depending upon the particle size distribution, particle characteristics, and interparticle interactions? So, one can, if you look at microscopically, so the particle, each particle is in contact with several particles, and how the heat flux from one particle to another particle takes place depending upon the contact interactions between these particles, and that is an area of interest, particularly that plays a significant role in thermal energy storage in particularly for solar energy systems where you have phase change materials. We also have the issue of current flow in lithium ion batteries. Again, that depends on the interparticle interactions, how the particles are connected with each other, so that your current flow is not inhibited. Imagine a scenario wherein, so you have particles like that. If you have if you have to have current flow from anode to cathode, from this side to this side, then you should have continuous connection between the particles. Imagine this particular particle is not there, then what happens? There will be the circuit is broken, so there will not be any current flow, which is a serious concern in lithium ion batteries. So, when you have lithium ion batteries, you have these anode particles, right. When lithium intercalation happens, the particles will swell and deswell. If it is graphite particles, typically the volume expansion happens up to 15%. So, they swell by 15% volume and then contract during charge discharge cycles. So, when this happens, these particles are subjected to fatigue loading, right, and they may actually break. And if they break, and imagine the connection is lost, then your battery capacity fades, right. That is one of the reasons why our batteries fade over a long time. If you are talking about new age materials, for example, if you want to use silicon as an anode material, which is becoming popular, right, the volume expansion happens up to 300%. It's a huge volume change, and because the system itself is confined, it experiences very high stresses. As a result, you will have these mechanical failures. So, you need to ensure such mechanical failures do not happen, so that the granular system behaves the way that it is intended to behave. So, the moral of the story that we have heard so far is that if you are interested in designing granular system, or at least understanding their behavior, we should first understand that they require special treatment, unlike conventional continuous materials. And the numerical approach capturing the physics of granular material is essential if you want to design a granular system, because first of all you need to understand, because doing experiments, the problem with these systems is you can do an experiment and you can measure the macroscopic property, but what is happening at individual particle level, that information is not accessible to us. So, unless you have a numerical tool which can allow us to understand what happens at the interparticle level, which allows us access to what is happening at the particle level, that improves our understanding of these behavior of these systems and hence the design process. So, that means the particle level interactions is essential, which allows us to understand the physics or mechanics of the system and helps us improve the design. So, here I will close with this slide showing some of the simulations done using a particle simulation technique called discrete element method. The first picture here, you can see initially there are two kinds of particles, green ones and blue ones. They are packed layer wise and they are subjected to the airflow from the bottom. So, that means air is flowing at certain velocity, and hence the particles initially were static were made dynamic, and that air is used to mix these granular systems. So, if your objective is to mixing of these granular systems, the objective will be what? Mixing them properly. What do we mean by mixing them properly? After completely finishing the mixing, you take any small sample, and if you look at the composition of particle A and particle B, it should be what you intended it to be. You might want both particle A and particle to be having 50%, 50%, and sometimes you might want only 70-30. So, is your mixing technique allowing you to do that? So, instead of doing experiment directly, one can resort to these simulations which replicates the experimental process as closely as possible. Okay. And here the second example here that I am showing is an impact. So, this is an impact simulation. So, you see a granular bed subjected to a high velocity impact of a spherical ball, and you can see how these particles are flying away depending upon the velocity that it is there. So, it is at certain velocity. So, the idea is that we can simulate these kind of things, and this is one simulation wherein imagine this as a soil and an underground detonation that is taking place. That means, you are providing huge energy of TNT. So, let us say a 1 kg TNT blast happened. Then how the particles will fly away? Typically, in understanding, so for example, if you are designing a truck which has to be mine protected or blast protected. So, what typically happens is they design the truck underbodies with a certain special geometry in order to minimize the damage. Okay. So, when we are simulating these things as a continuum system, they use the blast pressure as the load on the system. So, when the blast happens, there will be some blast wave that gets generated, and blast pressure, that pressure wave is going to go and hit the body. So, that is actually detrimental. In addition to that, there will be very high temperatures that are generated. That could also be creating a destruction to the body. But in addition to that, another important aspect that you will not be able to capture in continuum simulations is what happens when these individual particles will go and hit the body. They behave like bullets, right? Very high velocity, they go and hit the body of the vehicle. And when such a high velocity particle goes and hits the body, what happens? The overall picture is good, but what happens? These individual particles go and hit. So, if you want to simulate that, you should know what will be the velocity depending upon the depth at which this detonation is taking place, right? And the last simulation here is the powder bed spreading. So, I think I should close this fellow. So, here you can see this is typical laser powder bed additive manufacturing technique. It is a toy simulation, it is not really taking into account of all the features that are required, but it is reasonably well approximated. Here you have something called build platform, and you have powder particles coming from the dispenser here, and this is what we call requarter. The requarter is moving and the powders are spread on the build platform. Once the powders are spread, then you will use a laser to either melt locally or center the particles in order to make the component. This is typically what is followed in metal additive manufacturing. So, the quality of the product depends on how good this powder bed is, meaning the packing of the particles, is it uniform everywhere or not, decides the quality of the final product. So, that is something that one needs to keep in mind. So, I have just shown you a couple of examples of the simulations and the method that we are going to learn in this course, which allows us to do these kind of simulations is I have introduced. But we will, before we actually go to the doing simulations ourselves, we need to understand the method, how this particular method called discrete element method works, and what are the ingredients of this method, how one will be, you have commercial tools that are able to simulate this, but we need to understand the physics behind it, what are the equations that it solves and so on. That is something that we will look at in this class. Okay.